we will do some, you can call them remarks on Fourier transform. Okay, and those remarks, as I mentioned, some of them have applied value, so they are very good to understand some of the applications that you might study later, such as, for example, communication systems or signal processing, like when you take digital signal processing. And some of them are still of theoretical value, so basically they allow you to manage the Fourier transform of some special cases. So let's start. So number one, remember what we mentioned. It has to do with something that we already mentioned. Remember what we mentioned when we said that what happens when you have time shifting in time domain? Yes. So what happens to the Fourier transform in the frequency domain? It's multiplied by exponential, which eventually means that the magnitude stays the same, and the phase is shifted with a linear value, right? So the phase can change with something else, but in that case, the phase is changing with a linear value, okay? Now for all systems, so if I have a system, okay, if the input to the system, let's say x of t, and the output, let's call it y of t, okay? If, again, we are talking about, let's stick with linear time invariant systems, because otherwise Fourier transform would not even mean anything. You can only do a Fourier transform of the impulse response of a linear time invariant system, and in that case, that Fourier transform exists, number one, right, for the system impulse response, and then the impulse response in the first place has a meaning, and then in addition to that, it has a value, because in that case, you can go in frequency domain, as we mentioned last time, and to get the output in frequency domain, you multiply the input by the transfer function, which is the Fourier transform of the impulse response, right? Now, what I care about right now is not this, but the fact that if, okay, for any system, if the output, so basically y of t, okay, has more or less the same shape of input, okay, subject to two things, okay? Number one, scaling factor, scaling of amplitude, and the other change that can happen between the output and the input is linear phase shift. So the only difference between what I mean here has the same shape as the input subject to those two variations. It means that the output can be obtained from the input by some scaling, whether the scaling is positive or negative, is greater than 1 or less than 1, right? Which means this is in terms of the amplitude, okay? And the phase of the output can be obtained from the phase of the input, either it's the same or within a linear phase shift difference. In this case, we call the system distortionless system, okay? In this case, or we said F already, so we can say then the system is called distortionless system, okay? So it has a distortionless property, okay? The idea here is, okay, these things, they can be compensated again, and then you can obtain the input, right? So that's one reason why we say so. Or you maintain all the properties of the input within something that you can compensate, okay? So in that case, the system is distortionless. Now, if this is not the case, if the output has no relation to the input within those allowable changes in terms of the magnitude or in terms of the phase, then this means that the system causes distortion, and it's very difficult to recover the input from the output, okay? So for distortionless system, you can recover the input from the output. For a system which is distorting the input, right, then you cannot Given the output, you cannot recover the input anymore. Yes?
So only one of them has to happen, not
No. Within both of them happen. Okay, so it doesn't mean that this or that. I didn't say this or that. I said this and that. Okay. So the idea of, as I mentioned, the idea of a distortionless system for distortionless system. Okay, practically we can recover the input, which is x of t, from the output, y of t. So given y of t, I can recover the input. I can do some processing on the receive or the output of this system, and based on that processing, I can actually recover the input. If not, then practically it's very difficult to recover the input. Okay? Practically, we are talking practically. Okay? Now, can anyone tell me what does this mean in frequency domain? So scaling in time domain would mean scaling in frequency domain, right? Phase shift, do we look at phase shift from time domain or frequency domain perspective?
Phase shift from time domain. From time domain, so it would be like, from
frequency domain, right? So when you look at like amplitude in time, you can look at it as amplitude and frequency. It's the same. So when you scale something in time with a value A, the frequency domain amplitude is going to be scaled with the same value A, right? But then the problem is phase. Where do you have a good look at phase? It's typically in frequency domain. Why? Because frequency domain is the part where you have a complex representation. For practical signals in time domain, you have a real representation. So there is no phase, right? The phase only appears when you talk about frequency domain representation, and linear phase shift in frequency domain would mean that in time domain, this is time shifting, right? So basically distortionless system, so if I look at this, so all these two things that I mentioned, you can look at them. So the previous mentioned properties, not properties, sorry, allowable changes, okay, which is number 1 and number 2 that I mentioned previously, are stated from a frequency domain perspective, right? Perspective. Which means that if this is my system, right, and it is distortionless, then if I have x of omega as the input, the output is going to be somehow A multiplied by x of omega multiplied by e to the j omega some value t naught, right? Or you can call it whatever, j omega a, b, c, x, whatever. It doesn't have to be named t naught, right? It's just the slope of the phase, okay? So this is your output y of omega. So the output can be obtained from the input by some scaling and some linear phase shift. These are the two properties that I mentioned previously in the previous page, right? Okay. Now, if you look at this from time domain, so this is from frequency domain perspective. From time domain, if I have x of t, then the output, again, scaling is going to be the same from time domain. So it's still scaling, right? Yeah. So I will have a as a scaling multiplied by x of t plus t naught, right? Okay. And then this is going to be my y of t. Don't forget that if it was x of t minus t omega naught, this would have been e to the minus j omega t naught, right? If it's x of t plus t naught, then it's a to the j omega t naught with positive, okay? So the sign is the same. You inverse the sign when shifting happens in frequency and you go back to time, okay? Yes?
so the original equation has a negative here, right?
Yeah, the one where we used for the property was x of t minus t naught. So it produced e to the minus j omega t naught, right? Now if it's x of e to the j omega t naught, then it comes from t plus t naught, right?
Okay.
Again, you can put t naught as negative, then it becomes shift negative. So it's up to you, okay? So anyways, these two properties will map into in time domain. So this is in time domain. They will map into, again, amplitude scaling. Right? And the second property, instead of saying linear phase shift, it becomes time shift. Right? Whether it's a delay or advance. So positive or negative time shift. Okay? So from a time domain perspective, a distortionless system is a system that causes maximum those two changes, right? Scales the input somehow with like greater than 1 or less than 1, so it amplifies or attenuates the input, it doesn't matter. And the other part is that it can only shift the input in time, but it cannot do more than that. So if it scales the input in time, for example, that's not a distortionless system. It's a system which is distorted. It causes distortion to your signal, and it's very difficult to recover the original input from the output that you receive, okay? So this is like kind of a practical comment point of view, so keep it in mind. Whenever you are told that you are dealing with a distortionless system, you know immediately that in frequency, you can get the output by doing this to the input, and in time you can get the output by doing this to the input, okay? So immediately this implies that the maximum variation that you can do is time shifting and scaling, or in frequency domain, linear phase shift and scaling, okay? To get the output from the input. Now,
I was asking, why is it sometimes important for us to know if something is distortionless? Is it like
I already answered. Let me stop there before you suggest, okay? Let me stop you there, sorry, okay? So what I'm saying here is, what I just said is more or less the answer to your question. So because in that case, I know that I'm bound with only two types of variations, and these two variations practically are easy to recover from. If I know that the output is just a delay of the input, I'm going to just do an inverse time shift to retrieve the input. And if I know that it's simply a scaling, then I'm going to multiply by that. So eventually, to recover the input from the output, all I need to do is a simple system which is doing only two functions. Time shifting with some variable value maybe, okay? So you can adjust it the way you like, and amplification or attenuation with some variable value. And that's it, right? So that becomes much easier to do. And it's particularly of importance when you deal with things like filters, okay? When you deal with filters, for example, or when you deal with things like communication systems. So signals going through a channel, and your objective finally is to recover the original signal.
Yeah.
Your objective is not the output. Your objective is what was sent, which is the input to the communication system, right? So when someone sends you a message, you want to know what he sent, not what you receive, right? Because like ideally what you receive should be what he sent, but what you receive is some changed version of what that person transmitted, right? So you want to recover the original signal so that you get the message that he wants to deliver to you. Similarly, when you are filtering a signal, so filtering, do you know what's filtering, first of all?
Yes.
So filtering, the function of filtering is simply, this is like not like okay, omitting parts of the signal in frequency domain, right? And maintaining another desired part, okay? Ideally unchanged. So you want to omit, so if you have a signal that looks like this in frequency domain, for example, okay? Okay, and your interest is only in this part, so you want to filter out this part, what you should get from the filter should be something like this, okay? And so it should look similar to this exactly, right? And then the remaining parts will be omitted. This is the action of filtering. This is in frequency domain, so versus omega. This is when you look at the signal from a frequency domain perspective, right?
Yes.
So now your objective is to maintain the shape of this part, right? And to omit the other parts. They should go to 0. Okay, that's called filtering. This is the action of filtering. Okay, given that, for example, this was my desired part. Okay, so call it D or whatever. Okay, this was the part of frequency where I desire to maintain the signal or the system or whatever and with the same look. So now you can only maintain the shape if you allow those two things that I mentioned, right? Linear phase shift maximum, okay, and amplification or attenuation, right? If you allow something other than linear, so beyond linear phase shift, the shape of the signal is going to change in a way that does not allow you to recover the original shape. So if you do something non-linear, you will probably get something like this. The signal is going to change totally, even from an amplitude point of view, okay? If you allow non-linear phase shift, okay? So this is not something that you want. خلاص يا جماعة? That's why we are interested in knowing whether a system is distortionless or not. In fact, we are interested in designing systems that are distortionless, okay? Such that they allow the recovery of the original signal or the maintenance of the part that I'm interested in without altering it in a way that cannot be recovered, okay? So that's the first note, distortionless. They call it distortionless processing. In communication systems, they call it distortionless. In filtering or signal processing, they call it distortionless filtering. In communication systems, they call it distortionless transmission. So it only depends on what kind of application you are doing, okay? The other important note, and this one is kind of tied to theoretical calculation, is how to calculate energy from frequency domain. So remember, okay, from time domain, yeah, we know that the energy of a signal x is equal to the integral from minus infinity to infinity, our signal x of t squared, and you integrate with respect to time. This is going to give you the total energy contained in the signal, right? So like something we started with at the start of the course. Now, what if I don't have the time domain? I have the frequency domain representation. Can I still calculate the energy without having to go back to the time domain? Yes. And the reason for that is something called Parseval's theorem. Okay. So this is a very important theorem. Okay. So Parseval's theorem says that this same thing, E of x, the energy of a signal x of t, can be obtained. So in time domain, it's equal to the integral from minus infinity to infinity, x of t squared dt. And the same thing can be calculated from frequency, subject to a scaling factor, so 1 over 2 pi, and you integrate from minus infinity to infinity, x of omega squared d omega. And keep in mind that once we go, even from a practical point of view, once we go to frequency domain, this absolute value becomes very relevant, because in this case, you are dealing with only the magnitude of your Fourier transfer. The phase is not included. So to calculate the energy, you only care about the magnitude of the signal. The phase does not affect the energy, okay? So that's why we have the magnitude squared of your Fourier transfer. خلاص يا جماعة? So this theorem is very important, and in many cases, it's easier actually to calculate from frequency domain, because the frequency domain in many cases looks simpler as a function to integrate, okay? But you have both options. You can do it from time or frequency domain. Now,
So if I convert it to time domain and calculate the energy from the previous equation for the time domain.
مفيش previous. هي دي equation بتاعت التايم domain.
Okay, from this one.
Yes.
It will be the same, right?
مكتوب لك equal اهو. امال equal دي معناها ايه؟ Okay. So we do it from time domain or you do it from frequency domain, it's the same thing. You will get exactly the same result. That's the theorem. The theorem says that if you do this, you can calculate the energy from frequency domain. If you do this, you can calculate it from time domain. And of course, it's the energy of the same signal. So it should be the same. Whether you look at the signal. Again, when I look at you from here, انت اسمك ايه؟
Amir.
Amir, انت Amir. When I look from you to the side, let's say the side is frequency domain, you are still Amir. تمام? So it will not change. So the energy is going to be the same. تمام? Okay. Any other questions?
Is there a similar rule for like the Fourier series, like discrete?
Sorry?
Is there something similar for Fourier series, or
قلناها في الفورير
you
series.
just add them, right?
قلناها في الفورير series. Summation of the square of the dn. We said it. It's there. Review your lectures. You will find it. It's the same, and it's called the same. It's called Parseval's theorem. خلاص? So yes, it exists for the Fourier series, and we said it earlier. If you go back, you will find it. Okay. So that's another important kind of within the remarks, because you cannot categorize it as a property or whatever, but it is an important theorem that you have to keep in mind, and it's useful in solving several problems. Okay. Another important thing before we move to the last applied part. This is again another theoretical. Okay. How to find the Fourier transform, not series, of periodic signal. Okay, how you can do that? Okay, so if you are given, for example, a square wave, right? So, and it's periodic, so it keep on going and coming, periodic, repeated. Okay, and then you are asked to find the Fourier transform for that. How can you find the Fourier transform for a periodic signal? Of course, if you try the integral, it will not work. Okay, because take that square function multiplied by e to the j omega and integrate from minus infinity to infinity. The integral exists from minus infinity to infinity. But what's the value? I don't know. Right? Yes?
So you should have like discrete values, right? So I think you will have like delta values at the points of the discrete values.
Yes, that's you are anticipating what's going to be the result, right?
Yeah.
But I want to know how you can do it.
Mathematically?
Take a period of the wave تاخدها من ال so this is basically a box wave that's shifted down. ماشي. Like it's a tray basically of boxes but it's shifted down. So you take one period from like the bottom, from the middle of the bottom part to the other middle of the middle
Okay.
part.
Okay. بعدين.
Which is this story. And you integrate it.
And then after you integrate, أنا مش مشكلتي إنك you take this and integrate. Okay. I want to know why you will do this. بلاش, let me put it the other way. Why you will do this? انتوا الاثنين بتتكلموا عن نفس الحاجة. You are saying it's periodic, so I assume it's gonna be discrete, right? Why?
Why is it periodic?
Why is discrete if it's periodic?
Well, because it's periodic means it has a certain frequency and it's one only frequency, not a multiple frequency.
Periodic signals have only one frequency.
No, yeah,
You analyzed them
not
and you found that they contain multiple frequencies.
But
they are discrete.
Yeah,
frequencies, right?
and
So that's the reason. So you are close to the answer. What's the answer? Why?
Why are they like?
Remember.
Harmonics.
Why you have the discrete values? Okay. Why you have the discrete values? Not why they are discrete frequencies. Why you have deltas? Tamam? Okay. So let me answer. I mean, you are getting to the answer. You are telling how to do like the initial mathematical calculation, but you did not get to the essence of it. So the essence of it is that we know that this signal can be represented as summation, okay, of dn multiplied by e to the j n omega naught t, right?
Yes.
We already know that this is a true equation, right? Okay, and the summation from n equals minus infinity to infinity. So if I want to get the Fourier transform of this, I should actually be getting the Fourier transform of this, right? And that's a much easier Fourier transform to get. Why?
Because you know the Fourier transform
of e to the j omega, right? And d is constant, right? So you know the Fourier transform of any exponential function directly from the table, right? And we studied it in the properties, right? So immediately you can figure out that the Fourier transform of the e to the j n omega naught is going to be a delta at what location? At omega minus n omega naught, right? So this is going to, in the Fourier domain, right, is going to be delta at omega minus, so basically at delta at n omega naught, right? And since the Fourier transform is linear, the summation stays, and the dn stays, right? Correct? Okay, and this is from n equals minus infinity to infinity. So x of omega is equal to, I remember that in that expression, we had a pi factor as well, right? So e to the j omega naught t, when you take its Fourier, it becomes pi multiplied by delta of omega minus omega naught, right? That's what we studied, or you look it up in the table, right? So there is also a pi factor here, okay? That's when we do the Fourier transform. So this is time domain, right? And this is frequency domain. Okay? So simply, now if you want physically to understand why it becomes deltas, right? Eventually, because what we see here is a summation of deltas at different locations, right? Why? Because remember, in time domain, right, when we looked at periodic signal, we said that they can be analyzed into summation of cosines, right? And cosines simply are a summation of complex exponentials, right? And those in the frequency domain are discrete frequencies, so they only exist at finite, like at discrete frequency values. That's why you have deltas at omega naught 2, omega naught 3, omega naught 4, omega naught, and so on. Not only that, the values of those delta are actually just a scaled version of the Fourier series coefficient, right? So simply for that periodic signal, what you need to do is get the Fourier series coefficients and then represent them as multiplied by delta at the n omega naught locations and scaled by a factor pi. That's it. Now, if it was f instead of omega, there is no factor. Okay? So that's just for your own notation. Okay? Okay, so that's how you get the Fourier transform of any periodic signal, capitalizing on the fact that the periodic signal can be represented by this summation, and for this summation, you already know how to get the Fourier transform. Because for every complex exponential there, it's simply a shifted delta multiplied by pi, right? And then the other parts, this and the summation stays because of the linearity. I have a sum of exponential, then the Fourier transform is the sum of their Fourier transforms, right? And each one is scaled by a factor. Then in frequency domain, it's scaled exactly by the same factor because of the linearity of the Fourier transform. خلاص يا جماعة? So this is why, and this is the physical meaning, when you look at the Fourier transform of periodic signal, you find it as delta functions. The reason is, I know that the periodic signal is a sum of discrete cosines, discrete frequencies. So discrete frequencies are going to be represented by delta signals in the frequency domain. They exist only at single frequencies, right? I mean multiple of them, but only there is no continuous spectrum. It's only at certain discrete frequencies. خلاص? How many of those frequencies? Typically infinite, right? Because typically periodic signal will have infinite frequencies. Right? It's only the spacing between them and so on. خلاص يا جماعة, any questions about this? Okay, so this is how you get the Fourier transform of periodic signals. خلاص? That's another note which is of theoretical value. Okay? And one of those interesting periodic signals, let me see if I have it here, is the train of impulses. You did it also in the tutorial, right?
Yeah,
I think I have it somewhere. Anyways, yeah, okay. So the train of impulses. So for example, so example of this, okay. Why do we care about this? We will see later. Example of this is the train of impulses x of t, which is represented as x of t is equal to summation from n equals minus infinity to infinity delta of t minus n some factor t. So if you look at this signal in a time domain, you will find it what? Delta at 0 when n is equal to 0, delta at minus 1, at minus t when n is equal to minus 1, or equal to 1, sorry, delta at minus 2t, delta at minus 3t, delta at positive t, delta at positive 2t, positive 3t, and so on. So the difference between each one and the other here is capital T, right? And this is as a time domain signal, right? Delta functions that exist at spaces of t, right? Because nt, so put n equals 1, this becomes delta of t minus capital T, right? Which exists at positive t. Put n equals 2, this becomes delta of t minus 2 capital T. This is a delta that exists at 2t, 2 capital T, right? And so on. Put delta with negative values, you will get the other side, and you are adding all of them together. So when you add those deltas together, it becomes a train of delta as one function, right? When you look at the graph of that result of the summation, it's going to be delta, and then added to it another delta shifted, and then added to it another delta shifted. When you add them, it becomes the delta one beside the other, right? So you end up with this representation for the train of delta in time domain. When you take the Fourier transform of this, interestingly, this is a periodic signal, right? This is a periodic signal because it repeats itself every capital T. So when you take its Fourier transform, it becomes again a train of delta. So x of omega for this signal, so if you take Fourier transform, okay, is equal to 2 pi, equal to, instead of saying 2 pi divided by t, I'm going to write it directly omega naught. So it becomes omega naught multiplied by summation from n equals minus infinity to infinity, delta of omega minus n omega naught. And the relation is omega naught is equal to 2 pi over capital T. Okay? خلاص يا جماعة? So this is the Fourier transform of the train of delta. This is important, even though I put it here as an example, it's important because we will visit it later on in a few weeks, in a couple of weeks maybe, or less than a couple of weeks. خلاص? And you'll just keep this in mind. We will come back to it later because we will need it essentially in something that will come later. Okay? Last note is the, it's kind of like one step above the course, kind of an application again, is the multiplication with cosine, okay, or e to the j omega naught. So cosine omega naught t or e to the j omega naught t, right, in time. Okay, so basically I'm multiplying by a periodic signal, right? And that, periodic signal, a sinusoidal signal, right? Whether it's a complex sinusoidal, like e to the j omega naught t, or it's a real sinusoidal, so cosine omega naught t, right? This, in effect, is going to do frequency translation. And I'll tell you what I mean by translation, right? Okay? And that, when you study communication systems, is called modulation. Which is basically, my original signal, x of t, was something like this, right? In frequency domain. When I look at it in frequency domain, it looks like this. So this is omega, and this is my x of omega, my original signal, okay? When I multiply this signal in time domain with a cosine, or with a complex exponential, okay, I'm doing a frequency translation, which means that I'm moving this signal up in frequency, such that it becomes the same signal, maybe scaled a little bit, like amplified or attenuated, okay? And it's exactly the same shape. It's not wider or narrower, but my drawing is not that perfect. I'll try to make it better. Okay. I'm trying, ya jama'a. Okay? But the center frequency, instead of being around 0, the center of that signal in frequency will become that omega naught that you have in your cosine or in your complex exponential. So the signal is translated in frequency, right? They call this, in the world of communication, they call it modulation. What's the advantage of doing this? Imagine that me and you want to talk at the same time, and we allow the receiver to tune whether to listen to you or to me. So one way to do this is I talk, you are silent. You talk, I'm silent. But this way, we are spending a lot of time to convey our message to the receiver, right?
Yes.
Even though he's interested only in one of us, right? So he will take longer time to receive your signal. The other option is we talk together, but I modulate my signal. So I make my signal, I multiply it with a carrier after it comes from my mouth, while we keep yours as it is. So when they arrive to the receiver, he can just tune to this or that and ignore the other. He can listen only to the one at the higher frequency or the one at the lower frequency. This is what you do in your radio when you are selecting channels, or in your TV when you are tuning to the satellite channel, right? Simply the satellite is sending all the channels at the same time. How do you differentiate? The satellite or the radio station is putting them in frequency domain at different frequencies. And when you tune your receiver, it just looks at, for example, this frequency range only, and it filters out everything else. Or it looks at this frequency range for another channel, and it filters everything out. So it's going to listen to this particular channel, right? And it's not going to listen to this or that or that, okay? So this is called frequency multiplexing. We multiplex our signals, make them transmitted at the same time, but different frequencies, and then the receiver is going to be able to recover the signal. The essence is, aside from the importance of the application, right, which I mentioned right now, so this is useful for frequency multiplexing. Okay, so frequency multiplexing is going to be, for example, I have this signal, I have another signal at different frequency, I have a third signal, right? So this is signal 1, this is signal number 2, this is signal number 3. What I did is, signal number 3 is put around some carrier omega 2, signal number 1 is modulated or multiplied by cosine with carrier omega 1, and signal number 0 or 1 multiplied by omega 2, omega 3, and this is multiplied by omega 1. So each one of them is multiplied by a different exponential frequency, so they become in frequency separated from each other, right? And then at the receiver can simply tune to listen to this, or tune to listen to this, using a filter simply, right? But that's not the approach. It's not going to be a filter. I'll tell you what's going to happen in the receiver in a minute, okay? It's going to be something and then a filter. I'll tell you why, okay? So that's called multiplexing, okay? And then at the receiver, it can tune. The action of selecting one of them is called tuning, okay? Or in signal processing words, it's filtering out, okay? Now, there is a difference between multiplying by cosine and multiplying by e to the j omega naught t. What's the difference? The difference is the cosine actually is e to the j omega naught t plus e to the minus j omega naught t. So when you multiply a signal by cosine, so if I have x of t in time domain multiplied by cosine omega naught t, then what I will have is two versions of the signal. One at the positive omega naught and the other at the negative omega naught, okay? And each one of them is going to be half the amplitude of the original one. So it's scaled down by half. But the width and the shape stays the same. خلاص? This is in terms of frequency domain. While if I multiply x of t by e to the j omega naught t only, so complex exponential, then I'm shifting the signal as it is without any scaling or anything to the exact location of omega naught, and there is no negative version appearing in the frequency domain. خلاص? We described earlier that the negative version does not really represent that this exists in reality. You are still, this is the real signal that you have, right? And the other one is just for mathematical representation. It becomes useful when you do extra processing of the signal, okay? خلاص, we described it earlier. But physically, there is no negative frequency. Basically, it's just a mirror of the positive frequency where you split the power among them. خلاص? Okay. So that's the modulation. So when you hear about particularly AM modulation, it's simply that you have your signal multiplied by a cosine, and that means that you are translating it in frequency to an upper frequency or a different frequency, center frequency value. What's the usefulness of this? We mentioned it. تمام? But what if you want to recover? Actually, the recovery of the signal goes into two steps. So to recover, okay, an AM modulated signal, okay, you need to do two steps. Step one, okay, you multiply again by a cosine or a complex exponential, okay, تمام? By a cosine, it's fine. By a complex exponential, you have to make it with the negative value, so that you bring the signal back into the original frequency, right? Otherwise, what you will listen to is going to be, for example, if it was the voice of a man, you're going to hear the voice of a mouse, right? Right? Because you bring it to a very high frequency. So it's not going to be the regular thing. So you have to bring the signal to its original situation, and then you start listening to it, right? So the step number 1 is multiply again, okay, with cosine omega naught t. So let's take the cosine example because that's the practical example in reality, okay? So originally, this is what you will receive. This is the modulated signal, which is around omega naught, right? And its inverse version is around minus omega naught, correct? Now when you multiply this again by a cosine omega naught, what happens? This whole thing, right? This whole thing together is going to be moved around omega naught and around minus omega naught. So you will end up with what? Exactly. You will end up with something like this, right? This is the, I'm sorry. You'll end up with something like this, right? And okay, so basically in this one, okay, imagine that this red one is going to be centered again around omega naught, right? With a minus, and that blue one is going to be centered again around omega naught with plus. And what's inside the box? What's inside the box is the two half circles that you see there, right? The original spectrum of the signal. This whole spectrum with the positive and negative is being moved up to be centered around omega naught instead of being centered around 0, and down to be centered around minus omega naught, right? So you'll end up with this one, right? Being moved down, so, sorry, being moved up, so it becomes here, right? And this one being moved up as well, so it becomes here. Okay? So that's one shift. The two things have been moved to be centered around omega naught instead of being centered around 0. Here, both of them, if you look at the combined, you see it's still centered around 0, right? Okay, so we took this whole thing and we moved it to the right. Then we move it to the left also with omega naught, and you will end up with this added to this and another one up here, right? Okay, so basically the last step, the second step, so this is step number 1. Now you want to get rid of these guys, because if you only take this guy, it's exactly the original before modulation. Remember, the original before modulation was like this, right? So you want to only limit yourself to this guy, and you want to ignore those upper parts. How do you do that? This is the second step, filter. Okay, so you only take this, which is the sum of those two, but now they are multiplied by a quarter. So when you add them together, it becomes half the original signal amplitude, right? And these ones are a quarter, this is a quarter, and you get rid of them because you filtered them out, right? After the second step. So now you recover the original signal, amplify it, do whatever you like with it, right? Within a distortionless system, you can recover the original voice or the original message, okay? So that's called demodulation. خلاص يا جماعة? Those who will study communication later on, they will get exposed more into this. Those who don't, this is a basic knowledge. Even if you are a computer engineer, this is a basic knowledge that you have to know, right? You will get exposed to modulation somewhere. Okay? خلاص? That's the last out of the remarks that I wanted to discuss about the Fourier transform. And by this, we are done with the Fourier transform, and also we are done with the time for the lecture today.